do, thank you. Hi, everyone. Okay, so I work for an organization called Forensic Architecture. We're based at Goldsmiths, the University of London. And I want to talk to you today about two things. That's a mechanism for deploying machine learning-based image classifiers to open source media, and a pipeline for developing new computer vision classifiers using synthetic image data that we can use to almost predict the monitoring situations of the future, to use image-based classifiers to find the objects of human rights violations much more quickly than human researchers are necessarily able to themselves. So at Forensic Architecture, we investigate human rights violations and state and military violence against civilians. We do that using open source research, digital modeling, video and image analysis. And we exist because of what we might call the open source revolution. Ubiquitous digital recording now means that human rights violations are more widely documented than ever. This creates new avenues for monitoring and the pursuit of justice and accountability, not least, as we saw quite recently in last year's issuing of charges by the ICC against a Libyan militia commander based almost entirely on open source evidence. Now, there was something interesting on the opening panel. Somebody said that it's not easy anymore to simply count the weapons systems that are owned by and owned up to by state actors. And if ever it was that straightforward, it certainly is less easy now. Non-state actors and proxy militaries and the breakdown of reliable oversight structures have made that the case. So this sheer quantity of open source material that's now available in the public domain is an opportunity for civil society to hold state and military actors to account, but it does also present logistical, technical, and indeed theoretical problems for those investigators and monitors. One of these logistical problems is going to be the subject of this short presentation. Oh dear, I realize I've been pressing on here and not on there. Okay, so, yeah, we'll go here. So investigations and monitoring in open source research often relies upon researchers' abilities to find specific objects or object class within a vast array of open source image material. Now, much of the material that a researcher views will not prove to be evidentiary. It may be partly or entirely irrelevant, but we don't know until we've looked. And given the absence of tools to improve this process, the default approach is still one of rote manual labor, and often the manual labor of researchers whose skills could be better and more fruitfully employed elsewhere. Our experience and that of our partner network tells us that this labor problem is widely acknowledged, and that it's broadly prohibitive to civil society's ability to hold states and militaries to account. Now, the potential for machine learning techniques of object detection to simulate and automate this perceptual task is already well demonstrated in a variety of other contexts, but it hasn't been applied to human rights contexts, and that's what we intend to do. At Forensic Architecture, it's our contention that where identifying a given object, for example, a particular military vehicle, within images is central to an investigation or a piece of research, machine learning techniques could reduce this specific time and labor demand, freeing up time and resources elsewhere. So we've developed a tool which we call triage to apply image classifiers to large quantities of open source video material. The tool is in beta, but we've already deployed it in the service of 2 of our investigations successfully. We're looking to establish partnerships around investigative casework and to build momentum towards a public release of this tool, which our partners in the human rights world, partners like Amnesty and Bellingcat and Human Rights Watch, have already told us could well be extremely beneficial. So this is the user interface. It's not particularly exciting at this stage, but I'd like to run you through a simple and generic example. So first is the selection or sourcing phase, where we use search terms and data and dates to delineate a media space, essentially, to take a segment of the open source video material that's available. So that could be a segment of YouTube or Facebook. And that we hope will contain relevant material. So here, it's obviously quite a crude search for Syria tanks. And here we're searching YouTube, and we can choose some dates. So mtriage then samples the selected media space according to those search terms. It compiles a CSV file of the URLs of YouTube videos that may prove to be evidentiary, that we want the classifier to do a sort of pre-check for us to identify what a human researcher perhaps should prioritize their attention to out of that set of open source material. Now, in this way, triage, we should say, avoids downloading any video content from YouTube, ensuring that copyright and IP perspective, we're all covered. We're essentially doing nothing more than watching an awful lot of YouTube content very, very quickly, much more quickly than a human could. Next, the tool processes the sampled media space using a classifier. Those can be either generic classifiers that are available online, but we are, as we're going to go on to talk about, looking at using pre-trained classifiers that we have trained ourselves on synthetic image data. It's our intention to build and supply a suite of custom classifiers, and they could be for a particular chemical weapon object, a particular military vehicle object, a tear gas grenade, for example. Suppose that we choose a custom classifier that's trained to identify tanks. triage will process the media and return a prediction score for every frame of each video as to whether or not that image contains a tank. And those predictions are then returned in a graphic user interface that looks a little like this. A researcher is able to order videos according to different ideas of what's most relevant, and you can also modify the threshold at which the classifier suggests that a tank is there if we want to be more or less accurate. And an interesting thing to note about this, what's quite productive from our perspective, is that the classifiers don't have to be 100% accurate. They don't have to be the best classifiers available in the field because, of course, we deal in evidentiary practices, we deal in legal context. Our human researchers are going to be looking at every one of these results anyway. And the red lines that you can see there is where the classifier believes that a tank is in the image. If we click on that, you'll be taken to the URL in the open source media domain where that potentially evidentiary material is to be found. So you can see how very quickly we're able to save a lot of time for a researcher. So that's the deployment phase, and that makes use of image classifiers. But training these classifiers to do their job relies on training data. Let's say you want to train an image classifier to recognize cats. What you need is an awful lot of images of cats and an awful lot of images of not cats. You tell the classifier which are the cat images and which aren't. It begins to develop patterns around what it thinks cat-like objects are in those images. Now, cat images are very easy to find on the internet, as I'm sure we're all aware, but images of, for example, chemical weapons can be harder to find. These objects are less common than cats and less commonly documented. So that's where synthetic image data comes in. We've begun to experiment with the use of synthetic image data to make up the shortfall. Now, that is to produce thousands of randomized images of the object in question, and we do that by developing digital models of these objects and then situating them in a given environment. So here we have a model of a Russian T-72B3 tank. We put it in a simple generic environment. We can add more objects. We can make denser environments that offer a larger challenge to the classifier. Obviously, the more we do that, the better trained it will be. Sorry, I realize I'm just running slow, so I'm going to move on. The next object that we did this for was a tear gas grenade. Now, what we would do is look on open source media domains for sort of traditional modes of documenting that object. So here you see two very common ways that tear gas grenades are documented, and we would look to replicate those in our synthetic image training set. How do we do that? Well, we arrange camera positions in space, we build our model and re-verify the dimensions of that model according to the image material that we have to produce an accurate digital model of the object. We then place that. We then develop a workflow, which would introduce a number of variables to that object, so we can vary the amount of dirt and obstruction on it. Again, developing the way that we can train this classifier on more complex material, essentially. Similarly, we generate randomized photorealistic environments into which we then drop the object. And what that creates is scenes like this, which are highly photorealistic, and according to our training data, they are sufficient to train image classifiers to then go out into the wild and find these particular objects in open source media domains. So what that means is that, I'm just going to skip forward a couple here. So what that means, and I want to talk about the future a little bit here, and to do that I want to go back in time briefly. What synthetic image generation means is that we can produce substantially more images that are sufficient to train an image classifier to search for an object than there are images of that object in the wild, let's say. So here we have a chlorine gas canister commonly used by the Syrian regime against its civilian population. So imagine we're in 2014. We have relatively few examples of the use of this object coming into the public domain. As we know now, there are to be substantially more of these. Now, in software development terms, it's fairly trivially straightforward to automate triage to run over a preset media domain according to preset search terms, let's say once a day, and to pull in new results. So if we are to build a synthetic image data set of this object, using the process that I've just elucidated briefly around the triple chaser grenade, then what we can do is we can automate this search. We can train a classifier that's pretty good at finding these objects, and we can produce for our researchers a list of, say, 100 to maybe even 200 or 300 videos that we should check every day to see whether there has been a new instance of this chemical attack. And I think we can see then clearly what the potential applications of this could be. It essentially allows us to extend our predictive capacity beyond the objects which are already extremely well documented into those objects which are not yet. And a really good example of that is, I don't know if anyone read Bellingcat's reporting around the M4000 bomb that they've finally found open source media material on. Those videos had been online for around 6 years before human researchers were able to find them. Okay, so the tool is currently in beta, as I suggested, but it has been used and tested in investigative casework. I see that I'm down now to 9 seconds, so I can't really elucidate what those are. But we are looking for partnerships. We're looking to collaborate, and we're looking to build momentum around driving this tool towards public release. So my details are here, and for those of you operating in civil society and working in monitoring and investigation, I'd be really pleased to hear from you. Thank you.